Alrighty, let's talk about how to take derivatives of trig functions like sine, cosine, tangent, etc. Okay, we're going to start with the derivative of the sine function, and first we're going to look at it graphically. So what would the graph of the derivative look like? Here's the original function, f of x equals sine x, and you'll notice there's some tangent lines drawn in so that we can find the slope of the tangent line, because after all, that is what tells us the value of the derivative. Well, the slope is 0 at a few places. You can see those horizontal tangent lines. Those happen when x is at negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, and of course if we extended the graph of sine either direction, it goes forever, those horizontal tangent lines would still keep cropping up at all the odd pi over 2 positions. Alright, there's also some places where the slope is negative 1. We can see two of them on this part of the graph. The slope is negative 1 at negative pi and at positive pi. But again, if we continued it out either direction, we'd get some more places where the slope was negative 1. And there's some places we see where the slope is positive 1. There's one right at the origin, and then at 2 pi, looks like the same slope, and at negative 2 pi, same slope. And again, because the function is periodic, it'll happen every 2 pi. Alright, so we've got some values of our derivative. That is, the function has these slopes, 0, negative 1, 0, 1, 0, negative 1, 0, 1. And so the derivative, when we graph it, will have those y values, 0, negative 1, 0, 1, 0, negative 1, 0, 1. So if we try to draw a graph that has those y values at each particular x value, we might get something like this. You can see that the y values are 0 in the right places, the y values are negative 1 in the right places, the y values are positive 1 in the right places, and then I've just connected them with a curve. Of course, this may look familiar to you. It looks like the graph of cosine x. So the question is the derivative of sine x actually cosine x? Well, there's only one way to find out. Let's take the derivative. So we have to use the definition of the derivative. If f of x is sine x, what's f prime of x? Everyone should now be mumbling under their breath. The limit as h approaches 0, f of x plus h minus f of x over h. For this function, that means it's sine of x plus h minus sine of x over h. So what do we do with that? Well, here's where we get to dust off some trig identities from pre-calculus or from a trig class in high school. And we remember that sine of x plus h can be written in this really annoying way. Cosine of x, sine of h, plus sine of x, cosine of h. So we expand that out, and then we still have the minus sine x over h. And now I'm going to break this really long fraction apart. There's going to be one part that I've circled here in blue, and then the other part. So remember that when you have something plus something all over the same denominator, you can split it up because of the way fraction addition works. So we have the limit of that first fraction plus the limit of that second fraction. This does not look promising. We're hoping eventually this equals cosine x, but it's looking really unpleasant so far. This is the derivative of sine x. We want it to equal cosine x, or we think it might equal cosine x, but so far it's just a mess. So I want to point out that both of these limits here have h approaching 0. So h is the thing that we're worried about. It's the variable. So x, as far as we care in these limits, is just a number. It's a constant. So when you have a constant times something in a limit, you can pull that constant out. We'll factor out cosine x out of the first limit and sine x out of the second limit. So it looks like this. Cosine x times this limit involving h plus sine x times this other limit involving h. Now, ideally we would know what those limits are. We'd be able to compute them. However, if you try just plugging in h equals 0, sine of 0 is 0, so that first one is 0 over 0. Cosine of 0 is 1, so that second one is also 0 over 0. Both of them have a 0 over 0 form. So we need to do something else to figure out what those limits are equal to. I'll give you the answer, though. I'll sort of preview of coming attractions. Those two limits both have nice values. The first one is 1 and the second one is 0. That means all this mess just reduces to cosine x times 1 plus sine x times 0. So our derivative is cosine x times 1 plus sine x times 0, which is just cosine x. So we were right, the derivative of sine is in fact cosine. Okay, but don't take my word for it. We need to see why those limits are what I said they are. Why is that first limit 1 and why is that second limit 0? The first limit, we want sine of h over h to approach 1 as h approaches 0. We're going to actually figure this limit out using geometry, so instead of the variable h, I'd like to call the angle that we're taking sine of, I'd like to call it theta. So instead of h approaches 0, we have theta approaches 0, and instead of sine h over h, we have sine theta over theta. It's the same exact limit. So that's what we want to prove. What we're going to do is show that if theta is an angle near 0, cosine of it will be smaller than sine of it over it. Right? Cosine theta is smaller than sine theta over theta. We'll also show that sine theta over theta is smaller than 1. Now, when theta approaches 0, cosine theta goes to 1. When theta approaches 0, 1 stays at 1. And so we get to use this thing that you had hoped you could forget, the squeeze theorem. The squeeze theorem says if you've got three functions, small, medium, and big, and the small and big ones go to the same limit, that middle one will also have to go to the same limit. So that as theta approaches 0, sine theta over theta gets squeezed and has nowhere else to go except to head towards 1. But that's what we want. Yay! So that's what we need to do. Okay, so the squeeze theorem is going to be our friend here, but to use the squeeze theorem, we have to be able to establish these inequalities. And we're going to do that in class. So I will see you there. But first, here's a video question. For right now, just assume we're correct that the derivative of sine x is cosine x. And we are, in fact, correct, but we haven't proved it yet. But right now, assume that it's true. If that's true, what's the derivative of the function 3 sine x minus the square root of x? Right, so bring that to class, and we will do some geometry to get that inequality figured out. I'll see you there.